Okay, dear, welcome back. And you have started watching support vector machine videos, and we are discussing dual problem. And the concept, basic concept, I gave in the last lecture with a simple example of linear optimization problem. But in case of support vector machine, it is quadratic optimization problem. But philosophically, everything remains same, meaning that dual problem we formulate when solving the primal problem becomes difficult. Okay, and you see, although we solved one problem by hand, but the difficulties were that if you have insufficient information about the nature of the samples, whether they are support vectors or not. If they are not support vectors, means if they are not on the gutter of the structure of the classifier, then it is harder to formulate an algorithm which will solve the alpha i's. And if we do not have this, then we cannot get W, we cannot get this condition, etc., etc. So, just like in reality, we have seen that when somebody is trying to outsource a particular product, then for him, the outsourced product has to be of minimum cost, and who is getting that product and that agreement that against this product I'll give you that much of money, for him or that company, that outsourced company, the objective is to maximize profit even with that that money. That is, lower bound of the bigger company will be the upper bound of the outsourced company. So that was a very simple example. But now we will try to, and there of course the objective function and constraint are to be designed appropriately. And now we will concentrate on actually our support vector machine, how we can formulate a dual problem. You see, this is our recapitulation. This is our problem. LP is actually the primal, the L corresponding to primal problem. That is Lagrangian function corresponding to primal problem, which is a function of parameter W and alpha, that is a Lagrangian multiplier, and B. Okay, and we are trying to, if you are trying to minimize with respect to W, then it becomes a primal problem, and the problem is this. Okay, and then you know how to optimize this. That is, you will have to differentiate with respect to W, and you will get the conditions. Now here also we have constraint. This is the constraint. Okay, and if the samples Si are the samples are on the gutter, then it becomes equal, otherwise it is greater than equal to 0. That's the constraint. The problem has to be satisfied always. And then we of course told you that what does it mean. Constraint means actually nothing but since it is our quadratic optimization problem, you see due to the presence of this, then I have the contour like this, and as many samples are there, that many turning samples are there, that many constraint will be there. And constraint actually what they are doing, they are eliminating some portion of the feasible solution zone. Okay, so this has a feasible solution of all this, and then so these are actually eliminated. That is the meaning of constraint actually. Okay, and then our search space becomes narrower. Okay, that's it. And having understood everything about the primal problem, then our dual problem is actually maximize of the primal problem, but with respect to the alpha. Okay, that is with respect to Lagrangian multiplier. So essentially, maximize LD over alpha. This is same as maximizing minimizing LP over W. Okay, and we have you have already solved this. Okay, putting the value of W, you differentiated with respect to W, and then with respect to B. So there was a condition, this and this. Earlier we have done, and we have solved it perfectly, right? And the solution was of this form. Okay, that is, it turns out to be the maximization of the dual function, Lagrangian function with over alpha turns out to be the minimization of the dot product between these vectors. Okay, and here the constraints, you will have to be very careful. Constraints are alpha I, they should be non-zero. Okay, they will be 0 for samples but non-zero for support vectors. Okay, and this condition has also to be satisfied because these conditions are coming from primal problem. We solved the primal problem the other day, and these two conditions you have got, and they has to be satisfied. Okay, so these are the constraint, and this is the dual problem. Okay, now however, the this thing you have to remember that this is equation number 2. Okay, so if 2 equation 2 has to be a dual of equation 1, if, okay, let me see. If equation 2 has to be a dual of equation 1, then there must exist the optimum value W and optimum value alpha show that W optimum, we are representing optimum value as star, is the solution to the primal problem as represented in one and alpha star is the solution to the dual problem. And primal problem equals to dual problem equals to L okay. But in general, in our case, yes, this is the case, but in general the optimum value of optimum solution of the dual problem less than equals to primal problem, optimum value of the primal problem. that is, again, if you just recap your that software outsourcing idea, primal problem wants to minimize the cost of production, right? And the dual should be less than of that cost of production. Then only they will outsource it, right? At the maximum, it could be equal, but it always normally should be less. Okay. That is in general that. And I will also can show you that this is the case. This is the some of the ideas we have taken from just convex optimization. They are very straightforward convex optimization theory. And since you may not know, we are just telling the necessary part for our problem. Okay. So that means, what is the meaning of this? That means maximum of minimum max mean less than equals to min max function. So max min function less than equals to min max function. Okay. So this is actually, we can show you with an this actually with an concrete example. So if, this is actually always true. Is true for any function. Okay. For any function. Now let us test it with a specific specific indicator function. Okay. Indicator function. Since by this time you know we are very conversant about indicator function, let us test it with the indicator function. Okay. So example, testing. Okay. Max over y belongs to 0 and 1, and then say mean over x, which also belongs to 0 and 1, indicator 1, x equals to y. So that means if x equals to y, then the indicator function is telling it will be 1. That is, if this is true, it will be 1. And then that less than equals to, we are testing. Okay. We will see that whether what I am writing is true or false. Mean of indicator x equals to y. Okay. Now let us test. So max of mean x equals to y less than equals to mean of max x equals to y. Let us see. What is this? See, minimum. What is the minimum of 0 and 1? 0. So max of mean this equals to actually 0. Okay. And what is the minimum of max of this? The indicator function. Okay. Okay. X equal to 0, 1. So x equals to y. Okay. What is the maximum? X, that is y. And you see 0 less than 1. So test successful. So we have taken just an indicator function, and we try to show you that the optimum dual value, functional value, will be less than equals to optimal primal value. Okay. So this will hold good always, and moreover optimum W and optimum alpha must satisfy KKT condition, very conditions. So that is so called very famous Karus Tuskar. So Karus in 1939, you see, and they in 1951 developed this condition. So as I told you, that convex optimization theory is very well mature, developed field, and they have a lot of mathematical proof and formulation. And this KKT, they told that one dual problem, which is maximization of the primal problem, which is a minimization problem, if really there has to be dual, then they must satisfy the following conditions, which actually we understand, okay, in our case, okay, equal to 0. So this will be 4, then alpha sub y is the level, okay, then W dot sub I plus B minus 1 equal to 0. Now see, in a generalized way, if I just write down, this is in terms of parameter W. So then what it is telling, the Lagrangian multiple alpha I times level, and this constraint will be equal to 0, and Z I W will be less than 0 and greater than equal to 0. So these conditions are to be satisfied if, and these are very, very important, because when we will actually develop the algorithm based on our dual problem, okay, then we will see KKT conditions, satisfying KKT conditions. Actually these conditions are so important. This in general we have written, this is the KKT's condition, okay, okay, and here also these are the KKT conditions. You can see the similarities. So they must be satisfied so that this will be a dual problem of this primal one, okay. So that's the story about the dual problem. Hope you have understood the concept, that why we need dual problem and how to develop a dual problem. We have not yet solved it, right? We have just developed the problem, and we will solve it in the next lecture. But before that, we will try to understand that what is how robust the support vector machine is, and how to test its robustness or increases its robustness, right? The concept is actually called the soft margin support vector machine also, okay. It's also called soft margin SVM. So what is the idea? Idea is, suppose this is my negative class, this is my positive class, and we have some samples like this, but there are some outliers. Okay, so this has to be here, but due to some noise or whatever, it may always happen. This is inside the gutter. Okay, and likewise from the other class, some samples may be an outlier for this class. Then how to solve, and then let us see in generalized way. This is zeta, let us call it not excellent, zeta. Okay, I is the distance of the outlier from a particular class. Then how to actually minimize that that error, creating robustness. This is similar to as actually how to regularize support vector machine. See, the idea is very simple. Take the original problem, primal problem. Let us take the primal problem. So what was the problem? To minimize over okay, of course, and B was there. Plus we attach some constant C and put it I equals to 1 2m if that many outliers are there. Okay, let us call it n because it should not be confused with sample size. Okay. So what we are doing, we are trying to minimize this. Okay, this is a minimization problem. We have attached a constant term and then that distance of the outlier from the gutter we have actually. So we are actually, in the sense we are penalizing. Okay, we are minimizing this. Okay, so if there are outliers, then with a constant C we are penalizing, and then subject to the constraint y suffix I w, then plus b greater than equal to, you see, 1 minus zeta I. So we have kept as it is. So what is the equation number? It would be 8. Where zeta I greater than equals to 0. Okay, I equals to 1, 2, 3 up to n outliers. Okay, so we have in the problem itself with constraint we have put this zeta I so that we can solve it in the primal problem as well as in dual problem. That we are going to do it in the next class. So concept is very easy, isn't it? That if you have outlier, just try to minimize that cost of the outlier by penalizing by term C. So how to evaluate C? How actually C will influence in the constraint in the dual problem, we are going to see it. But if you understand the concept, is very, very important that just by adding this term in my objective function, which is a minimization problem, okay, with constraint 1 minus zeta, okay, 1 was there minus zeta, okay, then where zeta equals to greater than equal to 0 is a non-negative parameter, okay, we can actually regularize support vector machine or increase the robustness. That we will see in the next class. So thank you for your attention. Have a nice day. Be safe. Bye bye.